Hello students, myself Dr.A.K.Thakur, Department of Math, Dr. C.V. Raman University. This is my mail ID. Today our topic is Laplace transform and their elementary formulas. So let us start from the definitions. This is the definition of the Laplace transform. Suppose L of ft be a function of t defined for all positive value of t, then the Laplace transform of ft is denoted by L of ft is defined by L of ft equal to 0 to infinity e to the power minus st ft dt. Provided that the integral exists, s is a parameter which may be real or complex, let L of ft being a function of s written as f bar of s. L of ft equal to f bar of s, which can also be written as ft equal to L inverse of f bar of s. Then f t is called the inverse Laplace transform of f bar of s. Here the symbol L, which is the Laplace operator. There are some conditions of the existence of Laplace transform. The Laplace transform of ft, that is 0 to infinity e to the power minus st ft dt, exists for s is greater than a if ft is continuous and limit t tends to infinity e to the power minus st ft is finite. Here is Laplace transform of some elementary functions. The direct application of the definition gives the following formulas. L of 1 is 1 by s when s is greater than 0. L of t to the power n is factorial n divided by s to the power n plus 1 when n equal to 0, 1, 2, 3, 4. L of e to the power at is equal to 1 by s minus a. S is greater than a. Suppose L of e to the power minus at, then it becomes 1 by s plus a. Next, L of sin at is a divided by s square plus a square when s is greater than 0. L of cos at is s divided by s square plus a square when s is greater than 0. L of sin hyperbolic at is a divided by s square minus a square, and L of cos hyperbolic at is s divided by s square minus a square. So these are some elementary functions and their Laplace transform. Now we will discuss some examples related to the elementary properties of the functions. Suppose we have to evaluate the Laplace of 1 is 1 by s. So by the definitions, 0 to infinity e to the power minus st, and here the function is ft equal to 1. So put here 1 in place of ft, it becomes e to the power minus st divided by minus s, 0 to infinity. This is the integrations and limit as it is 0 to infinity. After substituting the limits, it becomes 1 by s when s is greater than 0. Now, second, suppose Laplace of e to the power at, 1 by s minus a. By the definitions, 0 to infinity e to the power minus st, and ft is e to the power at dt. After combining these two exponential part, it becomes 0 to infinity e to the power minus of s minus a t dt. So their integration becomes e to the power minus s minus a of t divided by minus of s minus a, and limited as it is 0 to infinity. After substituting the limits, it becomes 1 by s minus a. So this is the second proof of the elementary functions. Now third is similarly L of e to the power minus at, it becomes 1 by s plus a, as usual the proof number second. The fourth one is, suppose Laplace of sine hyperbolic at, a divided by s square plus a square. As we know that sine hyperbolic at is e to the power at minus e to the power minus at divided by 2, and cos hyperbolic at is e to the power at plus e to the power minus at divided by 2. So by taking Laplace both side, L of sine hyperbolic at, L of e to the power at plus e to the power minus at divided by 2, 1 by 2 outside, L of e to the power at plus e to the power minus at. As we know, L of e to the power at is 1 by s minus a, and L of e to the power minus at is 1 by s plus a. So after some simplification, and we will get a divided by s square minus a square. Similarly, we can prove that the Laplace of cos hyperbolic at is s divided by s square minus a square by the concept cos hyperbolic at is e to the power at plus e to the power minus at divided by 2. Now, the sixth elementary result is sin at equal to a divided by s square plus a square. L of cos at is s divided by s square plus a square. By Euler's formula, as we know that e to the power ix equal to cos x plus I sin x. So e to the power I ax t equal to cos at plus I sin at. On putting the value of x in place of x, at, so it becomes e to the power I of at. Now taking Laplace both side here, L of cos at, I sin at. As we know, L of e to the power at is 1 by s minus a. After simplification, we will get the result is like this: x divided by x square plus a square plus I of a divided by s square plus a square. On equating the real and imaginary part of these equations, we get L of sin at becomes a divided by s square plus a square, and L of cos at is s divided by s square plus a square. So this is the Laplace of elementary functions. Now the last one, L of e to the power a t to the power n equal to gamma of n plus 1 divided by s to the power n plus 1, or factorial n divided by s to the power n plus 1. Very simple. Here ft equal to t to the power n. So putting the value of, in place of ft, t to the power n. So integration becomes 0 to infinity e to the power minus at t to the power n dt. This is our integrations. Now putting st equal to u, so t equal to u by s and dt equal to du divided by s. On substituting these things, and constant should be outside, 1 by s to the power n plus 1 should be outside, 0 to infinity, and this is the part. By the definitions, we can write down gamma n plus 1. This is n plus 1 divided by s to the power n plus 1. In place of gamma n plus 1 can be written as factorial n divided by s to the power n plus 1. Here we can write here n plus 1 gamma n plus 1 equal to factorial n. So this is the last elementary result of Laplace transform. Now we will discuss some examples related to the elementary properties